Okay, we're back. This time we're evaluating limits algebraically. In the last video, we evaluated the limits on a graph and looking at an input-output table. In this video, we're evaluating the same limits without a graph, just by looking at the equations and determining what the value of the limit is. Okay, this will actually be the last video of the series. One video on the graph and one video on algebraically solving it. So after this video, you should be able to do the practice problems and start the quiz. So I think you'll find this to be pretty straightforward. There's a couple things to get tripped up on those. So let me remind you that when we're asked to evaluate a limit, I want you to think as the x value gets closer and closer to 3, what value does this function approach? Or if you want to think of this as a function, what value would the y value approach? If you want to think of it graphically, right? As the x value approaches 3, what does the y value approach here? And the y value is this computation on x, right? So the first thing you try to do when you're evaluating any limit is you try direct substitution. Doesn't always work, but when it does, it's easy. Substitution. That's what we're going to use on this first one. When does direct substitution work? It works when substituting a value, the limit value, into your function doesn't come up with anything undefined. One is an example of when you get something undefined, when you get a 0 denominator, right? Because dividing by 0 gives us undefined value. Or when we have a square root of a negative, right? Because we're not including the complex numbers in our problem here. So we are stuck with just the real numbers. So what happens if I substitute a 3 in for x? Nothing bad happens. I just get a value. And I think if I remember from the last video correctly, it was just negative 15. Okay, if you remember from the last video, this is just a cubic, right? And when you plug in negative 3, which was over here, you go down to negative 15, or positive 3, negative 15. That point was defined on our function. And since there's no denominator in our function, or no square roots or anything, all inputs are safe. You can substitute any value in for x, plug in any input, and you will get an output, a real output. So because it's a nice polynomial function, we know that this limit exists and that it's going to be, I think it was negative 15, but let's be sure, by directly substituting. So it's just as easy as finding f of 3, right? If it's defined for 3, then we're just finding f of 3, right? So we substitute 3 in for x. So this should be 3 to the third minus 10 times 3 squared plus 16 times 3. So that's 3 to the third, 27, minus 3 squared is 9 times that's 90, plus 16 times 3, 48. Okay, 27 minus 90, let's see, negative 63 plus 48, which gives us negative 15. There it is. That is what we expected because it's what we saw in the graph. Okay, so a limit is, a lot of times it's as simple as just plugging in that x value and simplifying. Okay, as long as nothing tricky happens like getting a 0 denominator, you're safe. So you might wonder, well, what's the whole point of having this limit notation when we could just write find f of 3? Because we can actually calculate what would be undefined values if we think of them as a limit definition. Okay, so let's move on to number 2. Now you might remember with number 2, we had a graph that looked something like this. Okay, we had this asymptote, which was, and that was at positive 9 for the x value, and our function was approaching negative infinity from one side and positive infinity from the other side. So we had an undefined value for our limit. And it turns out that that's the result when we look at this thing algebraically. If we try direct substitution, which is what we should always try first with limits, what happens? Well, if we substitute 9 in, our numerator becomes 81 minus 36 minus 12. That'll be a real number. But then we plug 9 in down here and we get 0. So we get some real number over 0. That's undefined. Okay. So, but we don't stop there with limits. Sometimes we can try to see if we can cancel this denominator somehow. Okay. It's going to be unsuccessful on number 2, but it's going to be successful on number 3. Okay. So for number 2, the way we might try to cancel x minus 9 is by seeing maybe x minus 9 is a factor of our numerator. So we try to factor our numerator. This one happens to be factorable, I think. So let's see. That numerator should factor factors of 12 that have a difference of 4, 2, and 6. And then I've got an x here and an x here. And then I guess the 6 would be negative, the 2 would be positive because my middle term there is negative, all over x minus 9. And this is completely factored, and neither of my numerator factors will cancel with my denominator factor. So we're done. We can't evaluate this limit without getting an undefined result. And when we look at our graph, it's consistent because our graph doesn't show a limit. One side's shooting off to positive infinity, the other side shooting off to negative infinity. These sides of the graph don't agree at 9. So we can say that this does not exist. DNE. Okay. So that limit doesn't exist. Bummer. That's okay. Sometimes they do, like in number 3. Now you might remember in number 3, when we graphed it, it just looked like a parabola. Okay, and there was this point when we plugged in -2. I think it was at positive 18 or something like that. Except that was an empty point, right? It was undefined right there. It was defined all the way up to that point. It was 17.99, 17.999, boom. But as soon as we hit -2 on the x-axis, and this is at 18 on the y-axis, it was undefined. Why? Because when you throw a -2 in there, you get a denominator of 0, and that means that we've got an undefined result. Okay, but the limit, if you remember from the last video, because the x value was approaching -2, the y value was approaching 18. The value of the limit is 18 because of the fact that it's approaching 18 makes this 18. Now let's show how we would figure that out algebraically. How do we do that? The same way we did the last one. We realize we can't just directly substitute -2 without an undefined answer. So we try to cancel this denominator, okay, by factoring the numerator. So let's go to work. This is going to be the limit as x approaches -2 of, let's see here, what can we factor out of my numerator? Well, I can factor an x out, and what would be left here? I'd have an x squared. Here I'd have a minus 5x, and here I'd have a minus 14 over x plus 2. Now I've got a nice quadratic here. Notice if that factor won't cancel with x plus 2, but that's okay. And some of you guys might be tempted to just cancel those x's out, cross those out. But remember that in order to take a term and cancel it out of your numerator and denominator, that term has to be a factor of your entire numerator or a factor of your entire denominator. X is a factor of my whole numerator, but it's not a factor of my whole denominator because it's not a factor of this 2 here. Okay, so just remember that, or try to anyway. So now we try to factor this quadratic, and I want factors of 14 with a difference of 5. Lucky us, 2 and 7 will do the trick. So I got my x there, looks like a minus 7 and a plus 2. Okay, look at that, x plus 2 is a factor of my whole numerator, and it's a factor of my whole denominator, so those divide each other out, and we just get a 1 there. So this is really just the limit as x approaches -2 of x times x minus 7, and we could go ahead and simplify that, why not? Oh, you're off the screen. X squared minus 7x. Now we ask, is it safe to directly substitute my -2? Answer now is yes, because we don't get that undefined result with the 0 denominator. So I can go ahead and substitute a -2 in there. -2 squared minus 7 times -2. And we get -2 squared, that's 4. -7 times -2, positive 14. We get 4 plus 14. Oh, 18, which is exactly what we expected it to be. Okay, so even though 18 was an undefined, 18 wasn't defined for that function because we got a 0 denominator, we were able to get to 18 just by doing some algebraic simplifying, factoring, and canceling. Okay, here's another hint. If you plug in -2, right away, if you just substituted -2 in here, you would get a 0 on the bottom, but you would also get a 0 on top. Okay, let's check that out. -2 cubed, that's going to be negative 8. 2 squared minus 20, right? So now we're at negative 28, minus 14 times negative 2 plus 28, so that would end up with a 0. So if you directly substitute and you get a 0 over 0, that means you need to try and factor and get one of your factors to cancel out so that you can eventually arrive at your result. Okay, so we have a real limit where we have an undefined function output, and that is a key idea in calculus. So limits are kind of abstract conceptually, but when it comes down to actually computing them, evaluating them, it's not too bad. It's a lot of algebra. Okay, so that's it for this series. That's it. You can start the practice problems now and start the quiz, and I will hopefully have the next series of videos uploaded at least a week before they're due. We only have 2 more modules after this, so we're almost at the end. So don't give up. You guys got this. I'll see you in Zoom. Bye.